Hello, I'm Adam Powell. It's a pleasure to be here at the MIT A+B conference. Today, I will talk about the subject of high temperature electrometallurgy for climate mitigation. And I'd like to first begin by acknowledging the many people who contributed to the research that is presented here in this talk today. So I'll be talking about electrometallurgy and energy systems, in particular, three examples of high temperature electrochemistry and electrometallurgy. One is the use of zirconia solid oxide membrane anodes, or SOM anodes, for metal production. In particular, I'll focus on solar silicon in the interest of time. Another is a magnesium air battery for shipping, rail, and aviation applications. And the third is a direct carbon fuel cell for bioenergy with carbon capture at very high efficiency. So to begin with, on silicon, there's a continuous drive, as we all know, to reduce the cost of solar energy and solar modules. We've broken the 25 cents per watt module about a year and a half ago, although the cost has risen somewhat in the last year and a half due to supply chain issues. But there's a projection that we could go well below 20 cents per watt, and for that we really need to continue the reduction in solar silicon costs. And in order to do that, we need to first back up and look at the overall flow sheet of solar silicon production. It's a relatively complex process, beginning with carbothermic reduction of silicon dioxide to metallurgical grade silicon. This dramatically reduces the purity. It adds a considerable amount of impurities from the carbon material. So then we spend quite a bit of energy and effort to remove those impurities by conversion to chlorosilane, and then distillation, followed by chemical vapor deposition, very intensive process. This extreme energy inefficiency has motivated the use of other, as metallurgical routes to bypass this chemical vapor deposition and chlorosilane step. So, for example, you see here the use of liquid metals. In addition, one can also use electrorefining to directly refine metallurgical grade silicon into solar grade silicon potentially, though that requires first blending it with another metal such as copper. But what if we could eliminate the carbon altogether and use an electrolysis route to go directly from silicon dioxide straight to silicon? So that's what we are working on in this project here. So this is similar to the Hall-Héroult cell for aluminum production, which makes tens of millions of tons of aluminum every year at very, very low cost, $1 to $2 per kilogram. So it's a very similar concept, however, with a solid cathode here. The silicon product is solid versus the liquid aluminum that's produced in the Hall-Héroult cell. So the principle is similar, though. You feed silicon dioxide, it dissolves into silicate ions. This Si4 plus isn't quite right. It's more like an SiO4 4 minus. But that gets reduced to silicon at the cathode, and the oxygen travels right through a yttria stabilized zirconia solid oxide membrane. This is similar to the membrane used in the fuel cell. And then an anode on the inside converts that into oxygen gas, which is a very high purity oxygen gas byproduct. So one of the challenges here is that when you grow a solid electrochemically, any roughness gets amplified very quickly into what are called dendrites. So to avoid that, we periodically reverse the current, and in order to maintain a large high current bus and relatively low cost for the overall plant, what we do is we throw a switch periodically for one or more of the cathodes at a time, reversing the cathode to anodic potential, so that instead of plating silicon, we dissolve silicon, and that roughness dissolves rapidly, and then we can resume deposition again. This comes at a cost of some current efficiency loss, typically about 5 to 10%, so not a lot. But the result is we can grow silicon very nicely. So this is what the the cell looks like. This is a schematic over here in the center with the silicon cathodes and zirconia anodes in between them. And then a full-size cell would have a very large number of cathodes and a large number of anodes as well. The predicted energy consumption is about 20 to 25 kilowatt hours per kilogram, which is less than 1/10 of the 300 kilowatt hours per kilogram using the Siemens process for solar and electronics grade silicon. Looking at the energy balance, there are two energy stacks here. One of them is the resistance of the cell that leads to a potential. So we have the dissociation potential, which is the free energy divided by the Faraday constant. And we have other losses here in the anode and cathode leads on the molten salt and in the zirconia electrolyte. So we essentially have two electrolytes here. This is the liquid electrolyte and the solid electrolyte. Those electrolyte losses drop very dramatically at increasing temperature. But nonetheless, we have to keep them above the heat balance here, because those result in thermal energy generation. So the thermal energy absorbed includes the enthalpy of the reduction, which is above the dissociation potential. And plus the minimum theoretical anode and cathode heat losses and the specific heat of heating the silica to this temperature. So as long as we're generating more heat than we consume, then we can lose some heat through the sides and we stay in thermal balance. In terms of the cost breakdown, we have roughly equal cost between the raw materials, energy, labor, and assumption of other overheads here. The total operating cost less than $2 per kilogram. So this is a dramatic reduction versus the minimum possible with the Siemens process. Capital cost is about $10,000 for every ton per year of production. So a 160,000 ton per year plant would cost about 1.6 billion, et cetera. And so with a $3 per kilogram price of solar silicon, looking at about a 10 to 11 year break-even time on the plant. So a significant cost reduction in addition to eliminating the CO2 emissions and the other benefits of this is not even counting any sale of the high purity oxygen byproduct. So I'll turn next to a magnesium air battery. This is a battery intended for shipping, rail, and aviation. So looking at the cell level, we have a magnesium metal anode and a porous cathode made out of nickel, titanium, or stainless steel. We inject air through that porous material into a molten chloride salt electrolyte. And at the cathode, we have the reaction of oxygen plus electrons making oxide ions in the bath. At the anode, the magnesium dissolves and gets thinner over time, producing magnesium ions in the bath. The remaining nitrogen and some of the oxygen, they create bubbles which rise within this gap and provide quite a bit of stirring. And that's important because the solubility of these oxide ions, the magnesium oxide solubility essentially, is very low. It's about 1/2 weight percent. So we have to transport it out and then freeze the magnesium oxide out as we run this cell. So the full reaction is magnesium plus oxygen to magnesium oxide with an extraordinary theoretical energy density of 4,200 to 6,900 watt-hours per kilogram. And our projected energy density on the pack level, essentially on the container level, is about 1,500 to 2,000 watt-hours per kilogram, which is about 10 times the pack level energy density of lithium-ion batteries. However, we have a very high temperature cell because we have to run with these molten chlorides. Other molten salt electrolytes, such as hydroxides, carbonates, nitrates, etc., those will react with the magnesium, forming a magnesium oxide passivation layer. So chlorides eliminate that issue. Based on this, we have as I said, a shipping container as what we think is the minimum size. So this schematic here, this design shows 10 magnesium anodes in a stack, all within a single molten salt electrolyte bath in a 20-foot shipping container. So it's somewhere between 60 and 90 megawatt hours of electricity compared to about 3 megawatt hours that you can deliver from a containerized lithium-ion battery. So when we compare it to other battery and other technologies, I've got multiple technologies here. First, we have hydrogen, ammonia as potential fuels and fuel cells. We also have iron air batteries, aluminum air batteries, the Ambry battery, looking at the calcium shuttle with calcium antimony derived from liquid metal battery with a liquid metal anode in that case, and also lithium ion. So lithium ion has the highest round trip efficiency and the highest potential discharge rate, but at the cost of the highest cost and the lowest energy density of these. The magnesium air battery has a very low cost, very high energy density, and good round trip efficiency, about 50%, which is comparable to the hydrogen and ammonia, better than ammonia, but at the cost of low discharge rate. So the cell that was shown in the previous slide would discharge over about 500 hours, which is about how long it takes to get about 3 weeks, about the time it takes to get across an ocean in an ocean-going vessel. So we have demonstrated discharge. We have demonstrated the ability to withdraw the magnesium oxide using directional solidification. The last piece in this is to demonstrate recharging in situ by dissolving solidified magnesium oxide and reducing it to magnesium and oxygen at the electrodes. So you can see here why magnesium, that it has a relatively high energy density. Aluminum and silicon would not work in this chloride electrolyte, and titanium is much more expensive. Iron has high energy density, but very low energy, specific energy per unit mass. So magnesium has this very, very high energy density. As mentioned, we can rule out aluminum and silicon. It is very cheap also, that the magnesium oxide, which would be the feedstock for this, costs just 8 to 15 cents per kilowatt hour of battery storage. That compares favorably with about 10 cents for the hematite ore of iron oxide used in an iron air battery. The chloride salt is basically dehydrated seawater plus carnallite, so it avoids all of the complex ions that would react with magnesium. And in this molten salt, we have achieved 1.9 volt open circuit voltage, which is the highest magnesium air open circuit voltage to date for any magnesium air chemistry battery. Finally, very low cost. So the cost of the shipping container, the magnesium oxide, the electrolyte, other components, if we have to have a nickel cathode, assembly, even if assembly costs $50,000 to $100,000 per shipping container, we're looking at about $200,000 for 60 to 90 megawatt hours in a shipping container, which is about $3 to $5 per kilowatt hour upfront cost. So extremely low upfront cost for this battery. As I mentioned, it comes at the cost of lower round trip efficiency, somewhere around 50% round trip efficiency, and we will likely need to do some disassembly in order to recharge this battery. So it's very low upfront cost, somewhat higher operating cost for the battery. Our vision for shipping electrification is basically to load these shipping containers onto a ship, have the ship go across the ocean at the other end, swap out the batteries, and charge them on the shore. New ships use hybrid fuel engines with a generator and electric motor. So this would facilitate the retrofit using these batteries for electric propulsion. And they need to rebuild their engines every 10 to 15 years anyway. So we believe that we can not only have new ships using this, but also retrofit existing ships. So moving on, the direct carbon fuel cell is solves a challenging problem of how do you get solid carbon to react with a solid electrolyte in a fuel cell. So here we dissolve that carbon in a liquid metal, such as an iron or a manganese-based liquid metal alloy. We have that dissolved carbon then react at the surface of a cathode electrolyte tube with air inside. So we're able to capture a very large fraction of the oxidation energy of the carbon in the potential across that electrolyte tube. So the entropy of the carbon combustion reaction is very low. So these direct carbon fuel cells have potential efficiency, theoretical efficiency is very close to 100%. So we'll see how close we can get to that here. Looking at more detail, as mentioned, the carbon comes through the liquid metal anode, diffuses through, it reacts with oxide ions that come through the electrolyte here to form CO and CO2 bubbles that rise and stir the liquid metal to bring more carbon to the electrolyte in the anode. On the cathode side, we have air flowing through a porous support, then diffuses through the finely porous cathode and reacts to form, absorbing electrons to form these O2 minus ions, and then transfer through and react to form CO and CO2 bubbles, giving up their electrons on the other side. So we can capture the electrical energy across that cathode. On the right here, we show an actual structure that we fabricated in our group. We have a relatively coarse, porous support here that's about 5 to 10 micron pores made by cellulose particles, and a reaction layer here, which is the cathode. This is where we have our charge transfer reaction. That has 1 micron pores, then have a dense zirconia electrolyte layer here. Notice the theme with the zirconia electrolyte here, zirconia electrolyte for metal production. And the outer surface of that is in contact with the liquid metal electrode. So this is what it looks like in practice. We've just made these small kind of thimbles supported by the lanthanum calcium manganite electrode here. So you can see the very thin, it's about 40 microns of zirconia on the outside, and we used a Canthal wire for electrical connection here. So we mounted this inside of a furnace with a small crucible holding the liquid metal, and we used a graphite current collector on the anode, which, if necessary, if the carbon concentration drops in the metal, then that graphite electrode can dissolve into the liquid metal. We would use something like biochar or charcoal in the liquid metal in order to feed it typically. So here's the furnace where this all of this apparatus drops into it, and this would be has a reducing environment on the anode side, and it takes out the oxygen comes in, and CO2 goes out on the cathode side, the other side. No, I'm sorry. Oxygen goes in, CO2 comes out on the metal side. So just looking at the performance, we have open circuit voltage at up close to the 1 volt theoretical voltage of the CO2 formation reaction. This is at 1 atmosphere. though really in order to run continuously, we would have to run at high efficiency to avoid generating a lot of carbon monoxide. We'd have to run at somewhat higher pressure than this. So we'd want to put the ceramic in compression there. So in terms of performance modeling, this modified Evans diagram shows that we have a theoretical voltage around 1 volt at 10 atmospheres of pressure. So as we go to higher current density through the zirconia, that resistance generates heat, which reduces the energy available. As with the, this time we're flipped relative to the metal production. Our voltage, electrical energy that we take out has to be less than the heat that's generated by the reaction in order to maintain thermal balance without providing external heat, which we don't want to do. So we have to run at least 2.5 amps per square centimeter here, anything above that. And at that, we're running at about 65% efficiency at 2.5 amps per square centimeter and 1.7 watts per square centimeter. So our final efficiency would be somewhere around probably about 60%, which compares very favorably with the 30% that we run at for either the integrated gasification combined cycle or the chemically mitigated the metal oxide cell cycle we saw earlier today. So this is at 800 Celsius with a 50 micron electrolyte thickness. So this is much higher efficiency, and we also have a much simpler flow sheet than these other gasification flow sheets with just formation of the biochar, feeding in, air in, CO2 out. Very simple system. So, and this shows also the theoretical heat from the reaction. This is with some carbon monoxide generation, and then we lose some amount of heat to the gases going out. We recover some of it with a heat exchanger. And finally, we lose some energy through the terminal leads on the fuel cell stack. So this shows those losses. Nonetheless, even with all those losses, we can maintain thermal balance with 60% efficiency here. So in terms of the estimated power plant performance, the capital cost is about 1/3 that of other power plants with carbon capture. The fuel use is significantly lower because of the fuel cell efficiency. Carbon capture rate is very high because we're not trying to separate it out of the nitrogen-bearing combustion gases. We just have the separation with the water, which is a very simple temperature swing condensation. I believe this can scale down to a 6 to 10 megawatt stack of 10 cells. In about 40 cubic meters of cell size, so with balance of plant, et cetera. This is somewhere around the size of a large rail car. So this may be usable for rail propulsion, though that would be carbon neutral rather than carbon negative. Our likely maximum scale is 30 to 100 megawatts per cell, so 300 to 1,000 megawatts in an overall power plant. So, in summary, a high temperature electrometallurgy can deliver clean metal production for clean energy, with the example here given of silicon, but also rare earths, eliminating the perfluorocarbon production of those rare earth cells, and also magnesium, possibly aluminum as well, eliminating the carbon footprint of aluminum production. We can use a magnesium air battery for shipping, rail, aviation, and maybe even long-term grid storage with a very, very low upfront cost at the cost of low round-trip efficiency. And finally, the direct carbon fuel cell for low-cost, very high-efficiency bioenergy with carbon capture and sequestration. So I hope I've shown that these out-of-the-box solutions can deliver on some of the toughest decarbonization challenges out there. So Thank you very much. I appreciate your attention.